I'm Andrew Christ. I'm doing the summer EPSCoR internship in 2013, doing laser manufacturing and repair of wind turbine components, the preparation of it. So our problem is due to the harsh environmental elements that wind turbines are exposed to daily, the composite and components fatigue fairly quickly, which leads to failure in the material, which can cause obvious problems structurally and economically. So our solution to this is to create a mobile multi-purpose machine for the composites. This thing will be able to scale the turbine on its own, find where the damage is, and either replace it or repair it right on site. This is going to be a cost and time-effective method. This way you don't have to stop the turbine. Well, the blades will have to be stopped, but the turbine itself can be ready to go within hours. Saves money. And the idea is to produce as little forces as possible onto the turbine, because that's actually what caused some of the problems in the first place. So we don't want to propagate those issues. So how we're going to do this is with first finding the damage in the composite by 3D scanning. So this essentially takes a laser and scans over the surface, and a computer program will be able to tell where the damage is, how big the damage is, the size of the damage, and the shape of the damage. Then what will happen is, if need to be, if it's too big, it'll laser cut around the damage to remove that damaged material. If it's not too big, it can actually laser weld it by taking a filler material and heating up with the laser thermally, and just like normal welding, it'll be able to patch the crack or damage. If it does need to laser cut around the outside, after that, it'll use laser assisted machining to clean the edges to make sure it has a nice square cut. By doing this, it'll take a cutting tool like an end mill or some sort of sawzall, and a laser will be used to thermally soften the material right before the cutting tool, which will decrease the amount of forces on the cutting tool and material, and which leads to less vibration and forces. So this will clean the edges, and either a patch will be put in place and welded on, or additive manufacturing will be used by essentially sewing on a new piece of material one layer at a time by a very small melted material we lay down. So it'll crisscross pattern layer by layer until it's flush smooth. So my objective for this summer was to design and fabricate fixtures for the operating components of this mobile multi-purpose machine, understand how all the testing machines will operate, and then prepare setup for the testing of the materials. So what I've accomplished so far is a CNC mill has been equipped with a 500 watt fiber laser. That laser will be used to do all of the cutting, welding, system machining, all that stuff. A dynamometer has been set up to measure the cutting forces during testing. This will be our gauge on how well it's working. If the dynamometer is picking up a lot of forces during cutting, then we know that something's not right. We're not doing something proper, and we're not getting the results that we want. I set up a shielding gas system for welding. That's a necessity while welding. You have to have it or your welds can oxidize, or you just get poor quality welds. And then everything's all set up and ready for testing. So the cool thing about this is our mill's at the top right, or sorry, top left. The cool thing about this is it doesn't have to be just composites. This setup is universal. You can throw in any material in there and you'll be able to test it. So once the focus is off of composites, it can still be used for like the metal and the bearings and gears. You know, the heat treat or machine a little easier. So the top left picture is the mill with the 500 watt laser attached in it. The top right is a little bit closer to the view of the fixture I made to support the laser while operation. It has an angle mount because if you have the laser perpendicular while firing, it'll actually reflect back up into the laser, and you can ruin the optics that way, and that's a $50,000 optic, so we can't ruin that. And you also need to angle it while welding. That gives a better puddle while welding. It has a reflection shield, so any reflection off the surface while using the laser will be going onto the shield, which has been spray painted with black thermally non-conducting spray paint, so everything will be absorbed. The bottom left is our setup with the dynamometer amplifier. It's our data acquisitional system. This is what we'll use to measure the cutting forces. It'll be picked up by the dynamometer, sent to the amplifier to amplify the signal, which is then connected to the PC, and we can, by using a software program, we can see exactly what's going on, moment by moment while machining. The bottom middle is our laser generator. It's a state-of-the-art piece of machinery, touchscreen. It can be in local mode and remote mode, which is kind of cool. You can run it from a laptop if you want. 500 watts. It's a continuous waveform, so it also has a pulse setting. Air-cooled, water-cooled, pretty high-tech stuff there. And then the bottom right is the gas required for welding. It's just argon, 40 cubic feet of it with a regulator, and the hose hooked up directly to the laser, which has a shielding gas input port. You can just plug it right in, and it does what it needs to do.